And so let me share this screen. So today, and if you notice, we're currently on week 5 of the semester, right? Next week, February 14th, is your exam 1. So you'll have your first exam. This week, February 7th and the 9th, I'm introducing a new topic called singular value decomposition and recommender systems. Okay, so this should be a very interesting topic. So as I said, last week, we're pretty much at this point, we've completed the first phase of this, the very basic introduction to machine learning, right? So we've covered that. And so everything up until, KNN algorithm and also doing the performance. So now this week, we're going to start this idea of the recommender system. So recommender systems are basically, something that we're all familiar with because Amazon does it, right? So it's when they recommend products, or also it could be Netflix, right? What are other examples, I guess, of recommender systems? Music, like which Spotify. Yeah, all of them, right? So even a supermarket, I mean, if they develop an app, they want to recommend products to you. So that's basically the idea. So, so that's kind of what we're going to do. So we want to build a system that can recommend something. And at the end I will do the example based on movie reviews. So it'll be like movies like, The Matrix and based on user ratings. But then you guys will have your first real assignment, right? So your first assignment where you will have to do a recommender system for something else. So you'll have to find some data and then you'll recommend products, but it'll be the exact same algorithm. So we'll go over that. We'll be using Python, of course. So at the heart of recommender system, so there's a lot of ways that you can build a recommender system, but at the heart of it is something called singular value decomposition, okay? Or but SVD for short. So singular value decomposition is actually, maybe you've heard of it already. So it's from the field of linear algebra, right? So it's just a technique, and what we're going to see today, just the intuition of it. So I'm not going to make you do problems on singular value decomposition, but I'll give you enough of the intuition that you understand where this is coming from. Okay, that it makes sense. People have studied this. There's actually a theorem about singular value decomposition, and it just so happens that it has a great application to recommender systems. Actually, if you notice, this whole week will probably be recommender systems, and then next week will be singular value decomposition for dimensionality reduction, which we'll talk about as well. Okay. So before I get started, I guess, are there any questions? Any questions? All right, so let's go ahead and get started then. So I'm going to go to the whiteboard here, and we'll just start with some of the basics. So I'll start with some of the basics of just kind of where it's coming from. Then we're going to go into an example. We'll do an example with a little bit of data, and then after that, we'll get into our Python script, the data, which I've loaded already. Okay, so let's do that. All right, so first, let me put this in context, right? So we have machine learning, right? And as I've told you, machine learning can be divided into areas, right? So it's supervised learning, right? So supervised learning, right? And this is what we've been doing pretty much all in the first 4 weeks of the semester. Do you guys remember the other areas that I mentioned? So we've got unsupervised. What are some other areas? Huh? It has a test set. compare to. You're saying like two things that are not exactly correct. So they all have test sets, and then when you compare to something, that's supervised learning, when you have labels, right? The other areas are basically, we can say like sequential methods, sequential machine learning. And this is when you're predicting a sequence of events in the future. So I need to predict tomorrow to be able to predict Wednesday. And then I need to predict Wednesday to predict Friday. And then I need to predict Friday to predict, you know what I mean? So there's a sequence there. And those are sequential methods. And within that, there are reinforcement learning and, you know, Markov models, basically. Right. So now we've focused all semester pretty much on this supervised learning. And so what I want to stress is the difference, right? So what's the difference between supervised and unsupervised? Ignore the other ones, just focus on this one. So what's the difference between supervised and unsupervised learning?
Unsupervised, you give it data and tell it to learn from that without having a set to compare to.
I think you're getting the terminology wrong, but you have the idea correct. Okay. Right? So the set is the labels, right? So what we want to differentiate is that we have our data. In supervised learning, we have this, right? The X matrix and the Y vector. Yes. So you keep saying to compare it to, I think you mean this vector. All right, so then we have, you know, samples all the way to sample n, features all the way to feature n, right? And then this is the class, basically, the labels. So we said, you know, Setosa, Virginica, Versicolor, the three classes, so 0, 0, 1, 1, 2, right? These are called labels. And then this is the data, X data, right? So that's supervised learning because the model learns to correlate the data here, each sample, with a label correspondingly. Do you guys see that? That's supervised learning. Unsupervised is when you have only the X data. There is no Y data. So the Y vector does not exist here. So we have sample 1, sample 2, sample n, F1, F2, all the way to Fn. You guys see that? Why, though, would we have a situation like this? Why not just have everything be supervised learning? Huh? A what? Might not have a what? The Y vector. Yes, exactly. Why don't you have it? Hasn't been done before, right? So that you haven't been able to collect this data. Maybe it's really expensive to collect this data, right? You know, think about that. So it might be really expensive to collect that data. So these are then the models that are called unsupervised. You only have the samples and the features, and then you're going to learn something about this data, right? Now, usually in unsupervised, then we'll have something like a clustering method. Right, where basically what we do is, if you think this is a vector space, right? So if I go over here and I do S1, S2, S3, all the way to Sn, but I'm gonna keep it simple by just having three features, right? F1, F2, F3. When we have three features, we can basically plot it, right? So this is a vector space of size 3, right? You guys understand that? So it's R3, and then we have F1, F2, F3. Do you guys see that? We don't have labels like we did before, but we do have that every single one of these vectors, or these rows, is what? It's going to be a point in this vector space, right? So let's say that S1, S2, and S3, they kind of fall over here for whatever reason. But then we have an S5, it's another row or sample, and it kind of falls over here. And then S6 over here also falls. Intuitively, we can already see, you know what? These are kind of clumping together, right? That's called clustering, right? So they're kind of like creating their own little groups. Do you guys see that? And the more samples we had in each one, right, you know, the stronger the connection that we can say exists. That's called unsupervised learning. That's one of the things that we're going to cover later in the semester. You guys see that? But another thing that we can do is what we're going to do today. So we're going to have today a matrix of size n by m. And this matrix, again, once again, can have information, right? And so we're just going to analyze the information that we contain in here. So it's a type of unsupervised learning technique, right? So we're not going to apply clustering to this, and we're not going to apply the methods that we've seen before, like KNN. So we did KNN on this one, right? Because it was supervised learning, and then we could do something like something called k-means or clustering here. We'll study this algorithm later on. It's pretty straightforward and simple. But in the cases where we have our data, you know, just like this, some X data, we can apply other techniques. So today we're going to study the technique of singular value decomposition. Does this make sense? All right, and this is very specific to a type of task that we want to do. Okay, we want to do something. We're going to do some magic basically with math. All right, so math will allow us a very simple, as I said, I'm just going to give the intuition of how this works, and then we'll be able to do an example, right, and apply it. As I said, remember, we're studying recommender systems, right? So you can build this application easily in your, you know, in your company. How would you do it? Simple. You'd have a database, right? And that database has the information. So every night at 2 a.m., you run a cron job, download the data, run the recommender on the data, and then you're going to have basically ways of creating another, do the singular value decomposition, right, on the data. Then you're going to populate your recommender system database. And then in the morning, your user, when they come into the website, they'll have new recommendations. You guys understand? So that's basically the idea. Okay, so the key thing is we're going to need to have obviously this data, right? And this is going to be the ratings data. So we need to have ratings in there. So that the example that we're going to do is, as I said, users to movies. Okay, so now I've given you kind of the application of this. So let's get a little bit into the background just to understand how this, give you basically some intuition. Okay. So singular value decomposition, SVD, right? So let's singular value decomposition. Okay, so we're gonna think just that we have a matrix, just like we've done before. You've seen this in NumPy. Let me double check here. All right, so we have then our X, which is M by N. However, we've learned that you had some exercises, right, where you could perform some operations on matrices and vectors, right? You did that with the NumPy, right? In the first assignment, you played with that. Well, what you were doing with those matrices is basically what singular value decomposition is. So the question you might ask is, what does linear algebra do, right? So what does it do intuitively? And what does a matrix do to a vector, right? So we can take an example here, and this is just for intuition, so don't worry too much about it, but I just want to give you an insight. If you have a vector 1, 3, right, and then we have, and let's call this X, right? So that's a vector, and then we have a matrix A. So think this is a matrix M by N. Here I have a matrix A, which let's say it just has some numbers, 2 minus 1, 1, 1, and this is a vector and a matrix, right? What happens when you take A and you multiply it times X, right? It's gonna give you a new vector, right? It's gonna have, that has a type of an intuition, right? That you can perform operations and get other matrices and vectors. You guys see that? So that's basically where we're going with this, okay? So for instance, if we go over here and we think about, if we think about the operation now, it's gonna be y equal a x, right? And this is then, we can write it as 2 minus 1, 1, 1, and then the vector 1, 3. So this operation, basically, what you do is you take, this is just how linear algebra works. Let me grab another color. You grab this vector and multiply it times that vector, and then it gives you this value, right? And then you take this vector and multiply it times this, and it now gives you that value. It's kind of how it works. It's an efficient way of, think of it as you have a whole bunch of things and you're going to apply one thing to all of them, right? That's kind of what you were doing before. So if we do this, we're going to see that the result is, so 2, 1, minus 1, 1, 1, 3 should be, let's see, so this is going to be, if I do the operation here, so 2 times 1 plus 1 times 3, that's going to be, that's 2, 5, correct? So that's 5, so this is going to be 5. And then I do the other one, it's going to be minus 1 times 1 plus 1 times 3. So if I do that, that's going to be 2. So it's 3 minus 1, right? That's going to be 2. And that's 2. Do you guys see that? This is just pure mechanics. Okay, there's like a, you just learned this. I give you 30 of these, believe me, you'll know how to do it. Right? So it's pure mechanics. And you just learn the rule of how it works, but it's how everything in data science is done, because you have gigantic data sets and you want to apply certain things to it. Right? So that's what we did. That's kind of important, but what's more important is the intuition of what we just did here. So if you think about it, the intuition of what we just did here is that we have a vector space, right? Think of it that way. And we have the vector x, which, sorry, so this is very crooked. So we have that. Like that. So if we think the vector that we have initially is 1, 3, that's x, right? 1, 3. So 1, 3 is 1, 1, 2, 3. So it's going to be here. So usually you would write it like that, 1, 3. Okay, that's the vector. That's a representation of vectors in a vector space. When we multiplied it by a, which was 2, 1, minus 1, 1, right? When we multiplied it times the matrix A, what happened to vector X? It became vector Y. Do you see that? Vector X was basically modified by A to become Y. It's called a transformation. And this is very important because you're playing with the space. It's like, think of it as you have this space and then you're going to grab the space and stretch it and pull it and make it into another space. You see that we're transforming the spaces. So the analogy I could take is I can take this room, which is a cube, right? And it's represented by vectors such as these, create some kind of an A matrix, multiply all of that. And now the space that you guys live in would be different. It wouldn't be a cube anymore. It would be maybe a sphere. Do you see that? Or something else. And so now when you walk, instead of walking straight, what's going to happen? You're going to walk in a curve or walk up. You see that? So you change the nature of a space. And that's what I did here. So if you think about it, I have the vector x, this one, right? Represented by 1 and 3. You see that? I multiplied it times this matrix A, and what happens? It became 5, 2. So now it's 2, 3, 4, 5, 2. You see that? I changed it. And so what we're doing is, now we're changing things on a data set, a complete data set. Remember that these spaces, right? Remember that A if we go back to A, here, it is M by N, right? It is M by N. So that means there's a whole bunch of points in a space that is size Rn. You guys see that? Right? We've talked about this before. I did it actually when I did that scenario, right? So this space has 3 features, so it's got 3 of these axes. You see that? But I can have, instead of F3 all the way to Fn, so it makes it Rn, more spaces. But these are just vectors in this space. So I can multiply these vectors and arrive at different vectors. You guys understand the intuition? Right, so this is what we're doing here. So now that this is important because it can change the reference of all the points where they live. And so now we manipulate the world as in however way we want it, right? To maybe extract information a little bit better. So the effect is the following. So let's imagine now that we have a space, I'll show you why this is important, right? We have a space like this, right? And in this space, I had these points. You see, I have those points, but I also had some points over here. But if you notice, it's very difficult to kind of figure out what's going on, right? But what I can do is, if you think this space is kind of a, sphere, kind of a, let's say a perfect sphere, but I apply operations to it. And now what do? I convert it into, what is this called? I know it's not perfect drawings, so, but this is supposed to be a sphere. And this one looks more like what? An ellipse, right? An ellipse, yeah. So it looks, let me read you. So it looks more like an ellipse, right? So I've changed the nature of it where the axes of it are like this. So I'm going to take a reference point just like I did over here. And I have this and that. That should be straight. And then this and that. Do you guys see that? So I took pretty much the same thing I had over here, which was a perfect sphere, and I stretched it. The reference of it, the reference frame where the data lives. Remember, we don't really care about the space. What do we care about? These points. These are because they are basically the data that we want to initially. So they're all points. The effect of this is that when we stretched it, these points now are also moved in here, but in a different situation. What might happen now is, notice it made one axis bigger than the other. That's an ellipse by definition, right? But it makes it in such a way that it might separate this data a little bit better. So that now the effect is, I'm just going to change the colors of it. Well, maybe another color. So some of the points, the same points over there, basically ended up here. And then the other set of points, you see, so it helped to separate them out a little bit better. That's the effect that we achieve. Does this make sense, guys? Yeah.
There's not actually 4 matrices.
That's right. Yeah. So I'm just using an example. Yeah. There's no 4 axes is what you mean. 4 axes. A matrix of 4 versus a matrix of 3 is what you mean. Yeah. So no, in this case, it would technically be 2 because it's, like that. Yeah, so it's 2. But what I'm doing here is what's important, the intuition that's important is that I can manipulate a space that was spherical, if you will, and make it into an ellipse, for instance. And the goal of it is that I want to better separate the points. Here, there was too much overlap of them, right? But I learned something about the properties of them that I can group them a little bit better. So where would this be useful? Well, if I have a whole bunch of movie reviews, right, of the Matrix and everything, it's very difficult, or romantic movies or comedies, right? It's very difficult for me to figure that out by the name of the movie. But people are rating based on their preferences. So what's your favorite genre of movie? Thriller. Okay, your favorite? Sci-fi. Your favorite? Huh? Foreign? Oh, horror. Yeah, horror. How about you? Horror, sir? All right. Yeah, and you? Sci-fi. So you see but I didn't know any of that, right? So I didn't know that you guys were just labeling the movies that you like. But by doing operations like this became horror. And then this became, what was it, sci-fi. It came out. You see, it comes out, even though and of course, it's not that the system figures out, oh, it's the word horror. It doesn't know that it's horror. It knows something that when you look at it as a human, you'll say, oh, this is horror. Does that make sense, guys? So that's what's happening here in the background. And that's the intuition. So I want you to understand, because at the end of the day, I'm going to give you a little function, and the function you will take X, and the function will give you S, comma, VD, 3 matrices. But I want you to understand that these 3 matrices are actually this, vector and matrix operations. You're just multiplying things, okay? And the important intuition about it is that you have this one over here, a space like this, and then you transform it in such a way that now the data is easier. It's like you've looked, there's obviously an algorithm, right? So there's an algorithm that has a goal. It has an objective, right? And so that algorithm will take this as input, apply some transformations, which machine learning is pretty much that. You transform things. So you're going to take the original one, follow the goal of the algorithm, transform it into something like this, and hopefully your data is more separable, that you can identify these groups. And this is all unsupervised. So here in our case, as I said, you want to figure out horror, sci-fi, etc. Got it? Any questions so far? Is this making sense? All right, so now going back to the original idea then, let's go back to the original idea. Where was it? Yeah, so here again, so hopefully this makes more sense now. We have our data, we have our vector X, we multiply it times A, which I showed you the operation over here, gives you Y. If you notice, all that happened was the original vector X was rotated and then it was stretched. You see that? That's all that happened. So this had a magnitude, let's say up to here. We stretched it a bit, we rotated it a bit. You see that? If you notice, now we only did it for one vector, but you can do it for multiple ones. And if you notice, here we did the same. We rotated the vectors and we stretched it to create a new space based on the algorithm that we're implementing. Got it? Questions? So again, it's just intuition that I want you to understand. So what happened is we transformed one vector X into another vector, we rotated it and stretched it. And it turns out that there's actually special matrix. I'm not going to get into that, but there's special matrices out there just in linear algebra that are called exactly that. This is a rotation matrix or this is a stretching matrix. And all you do is you apply those, you will always rotate and stretch. Now in combination, obviously, you can achieve things like this, which is your ultimate goal, okay, to find new vector space. Okay. So what's important here is if you think about it, this was a coordinate system. Right? Cartesian plane, right? You learned this in high school. You spent a lot of time doing little graphs, right? And plotting things on. That was a Cartesian plane. It's a coordinate system. But what's important about coordinate systems are really important in everything, right? In all of science and engineering and everywhere, they're extremely important, okay? Coordinate systems, because they allow you to put your data, your thoughts in there and organize, and then do operations on them. So you take one coordinate system and you arrive at another coordinate system, where this other coordinate system hopefully will help you to better represent your data and learn more things about it, okay? So what we're going to learn now is then, hopefully you understand that intuition. So now we're going to make the jump to singular value decomposition. And basically, you know, people first just knew this, right? And then they started combining things and they figured out things and they came at the conclusion that you can have any matrix that is m by n and it can be decomposed, right? That's the word. It can be decomposed into 3 different matrices that are multiplied with each other, right? And this is what is going to become fundamental in what we're going to do today, because this is what allows us to find out these concepts, okay? These concepts that we want to do. So this matrix should be, if I remember correctly, this is m by n, and then this is n by n, and then this is going to be n by n. All right. And so, but that's not so important. What's important is that we can get these. This actually you won't have to do by hand. We will just use a function, right? So we'll have a function that will give you the 3 matrices. But what's important is, because of what we saw before, based on, as I said, based on the intuition, right? Based on this intuition that we can perform multiplications. Because if we can take this one and that one and get that one, then, you know, if you work your way back, given y, we can decompose it into a and x. You guys see that? 2, right? So that, you know, that's kind of in reverse. So it's the same thing here, except that we are going to decompose it into 3 specific things given the data, which are these. All right, and they have specific names. They sometimes in the math notation, they are written as this, right? So basically then you might see A can be decomposed into U, the diagonal, and V, right? But instead of using this notation, we're actually just going to say that a matrix X given the function of well, I should say singular value decomposition function will return S comma V comma D. And then these matrices, these 3 are also matrices, but now we're going to look at them because they are going to hold the information that we need for our recommender system. Okay. So I'll just write it out. You know, finally, there's a theorem. So the theorem says, so let's say singular value decomposition theorem. And you can just like accept that this exists, right? So it says every matrix, let's call it A, which is m by n. Notice this fits what we need perfectly, right? Because m is the number of samples, n is the number of features. They're not going to be the same. So that's going to be very, you know, it fits every data set that we have. So every matrix A, which is m by n, has a singular value decomposition. Okay, so that's basically the idea, and that translates, as I said, A then can be decomposed into, let's just say S, V, D. You know, you can think of it as a multiplication. Okay, so that's basically the background of it. All right, so I think hopefully that's the theory of it. And then now I'm going to do an example of how it would work. But are there any questions, I guess, so far? No questions? All clear? All right, so now let's go ahead then and do the example. And hopefully this will motivate it a little bit better. Okay. Huh? Sorry, what?
I think there's more people in the class.
Oh, I don't know. Yeah. All right. So let's do now the example, right? So we've learned basically, we have the intuition, I have X, I'm going to apply the function, and I'm gonna break it up into these three matrices, right? So let's now look at an example of movie reviews. And then when we look at the code, we will also use this example. So I've taken 100,000 ratings, I think, of about 7,000 movies and 600 users. All right, so that will be the data set that we will play with, right? Obviously, this smaller, but because I'm going to do this by hand. So we start basically with, I'm going to start with a simple example of our X matrix, our data, right? So it's going to be user 1, user 2. So that's you guys, right? So you basically use an application like, Netflix or something. User 5, user 6. Yeah, so that's a good question. So that's actually a really good question. So initially we have the data is reviews. Okay, so it's going to be review 1, review 2, review 3, right? All the way to review 100,000. In here, what you're going to have is you're going to have the user ID, followed by the movie ID, followed by the actual rating. Do you see that? That's what you get, and that's a good observation, right? So you could, if you were trying to had a label, let's say you have a label here that says positive, negative, right? So it's basically kind of what, although this would be very correlated with rating also. So it's actually a bad example of a label, but some label. You could then build a machine learning algorithm, where these are the samples and then these are the features and that's a label. You can definitely do that. You guys see that? However, for what we want to do, we're not going to decompose this correctly, right? This is not, so you brought up a very interesting thing that for us to use singular value decomposition, we do have to take data that looks like this and transform it into another format. Okay, guys? You guys see that? But the theorem still holds, right? So the theorem still holds in theory. Every matrix m by n has a singular value decomposition. So in theory, this one, because this would be m by n, would also, assuming there's, we ignore that because we need numbers. I guess these are numbers, but these are categorical. This could also have a singular value decomposition. However, we're not going to get out of that what we need. Okay, so we need to transform it into a different format. The format that we're going to use is where this is the users and this is the movie. So it's going to be, the matrix, right? And it's going to be alien, and it's going to be, I'm just going to write a few, Serenity, and Casablanca, let's do one more. Let's do You've Got Mail, right? So that's a romantic comedy. Do you guys see that? So for singular value decomposition, to give us the results that we need, we will need to transform it from something like this to something like that. Got it? All right, so this is how this would work well. And so now we have basically this, and we need to decompose it into our individual, the three matrices that we can get, S, V, and D. Any questions so far? Is making sense? All right, so what we need to do now is, then I'm gonna erase this. So obviously we need to write some code to make that transformation, but we'll do that when we go over the code. Now now this has ratings in it, right? So this will have, let's say 1, 3, 4, 5, 0, 0. This is user 7, 0. And then you have, say 1, 1, 2, 3, 4, 5, 2, 0, 1. You have 4, 5, 0, 0, 0. And then this one is 0, 0, 0, 0, 4, 5, 2. And finally 0, 0, 0, 0, 4, 5, 2. So just by looking at this, what could you tell me about the ratings? Remember, these are just the original ratings, right? So what would you're smart AIs, right? So obviously you have your own singular value decomposition algorithm, even though you don't know it, right? It's in there working inside. So what do you tell me? What can you tell me about this? What would be your conclusions? Yeah.
Very, very.
Sure. But what else? What patterns do you see between users or between movies? Yeah. Mm-hmm. Which users? Like users 1 through 4. Yeah, 1 through 4, right? So exactly, that's it. But you can tell, you're smart, right? So you can just look at it and you saw a pattern right there, jumps at you. Well, the question is, how can a computer do the same thing, right? And that's exactly what singular value decomposition will give us. The computer will be able to spot this. And then if you notice over here, there's another pattern. Do you see that? It seems that users 5 and 6 like Casablanca and You've Got Mail, which are kind of romantic comedy type of movies, right? So they might fall into another group, the romantic, let's say, right? So, and actually user 7 kind of as well. So what's important about this is, let's say, I drew user 7 as purple, right? And user 7 maybe is a new user, right? So it's a new user. And then they've already done, and then let's say they never rated You've Got Mail, right? But they did rate this one as a 4. And they've rated these as 0. Do you see that? So you're Netflix or you're your own company. What movies out of these 5 would you recommend to user 7? Keep in mind, user 7, and let's just say, okay, they haven't seen these. They've only seen one, that one. So of all the 4, this one, and this one, and this one, which one would you recommend to user 7 and why? Why? Because rated it highly, right? Yeah, exactly. So using this information, it makes sense. They like You've Got Mail, so you recommend You've Got Mail. If also, let's say that the user hasn't seen Alien and Serenity, but the user did see The Matrix and it rated it at 0. That's even stronger evidence that they don't fall into this group, but that they fall into this group. You guys see that? Now, of course, we can spot it because, you know, that's what we do as humans, right? We see these patterns. The question is, how does the computer do it, right? And that's where singular value decomposition comes in, because it'll try to create that same idea. It just does it, okay? And so now what we're going to say is we know this assumption that we have one initial matrix A or X, whatever we want to call it, and now we need to decompose it into 3. Well, as mathematically, it'll do this. It'll do the following. It'll create, let me do it. It'll create that. And let's say, I'm just going to make them a little bit smaller because I won't be able to fit them in. So those are the 3, right? Those are the 3 matrices that it takes the original one and it decomposes it into the 3 new ones, right? You guys see that? Well, these 3 new ones, let's call it U. That's the symbol, that symbol, and then V. It's actually V transpose, but I'm not even gonna use that notation. All right, so it just decomposes it into 3 things. Now the question is, what information is stored in here, right? So what we want to understand is that these 3, if I go to another slide. So now we had users, movies, and we're still in the first one, the rows are users, but now the columns are no longer movies. Instead, they're going to be vectors that represent correlations. You see that? So it goes back to that idea of what I did here. If you remember this idea, right? We had data in a certain way, but now we're decomposing it into these different little vector spaces where we can project our own data into them, and they'll hold things like grouping things by values. You see that? So that's all that's happening, and it does it automatically with just this algorithm. So if I go over here, you'll see what I'm talking about. So now I have users here, and this is just, it's no longer movies. It's whatever it is. It's a vector. So we're just going to say C1, C2, C3, let's say. And let's just say these are concepts. You guys see that? Concepts. So what it does is that it's going to take the users, and in these concepts, it's going to say whether that user correlated highly to that concept or not, you know, by putting a value to it. So in a sense, that concept will capture, we found these concepts, right? We found like sci-fi or action or thriller, and we found like romance. So basically that's what it's going to do. It's going to correlate users to these new things that it doesn't know the word for them, but it does know that they group together. You see that? That's basically all that's happening. So now you end up with users to concepts. Then we have the diagonal, which is something kind of different. And then here, we're going to have the third one. The third one, which will have as the columns, the movies. But now this is no longer the users. It is actually the same thing as this, a type of concepts. Okay, so concept. Okay, so what's great about this is then if we want to interpret it, we can interpret this as users, movies, and then we have the first one, right, which is users to the concepts can now be literally sci-fi, romance, and then maybe a third one that it really doesn't know what it is. Remember, it doesn't actually figure out the words, but what it does is, if we think the first 4 users, right, were highly correlated to like Matrix, Alien, Serenity, Sci-Fi, and very low correlated to all of this. So it's almost like it created a new vector, and now in this new vector, what would you expect here? These values should be high, right? So we're going to say S1, S2, S3, S4, S5, S6, right? So it's going to be 0.7, 0.9, maybe 0.5, 0.6, and then these are low. You see that? That's what it captures there. So now, just by looking at this one vector, we've identified sci-fi. And then with the romance, it might be the same thing. So now this was low for them here. So, but here it was pretty high. So again, we found sci-fi. For the third one, it might be all over the place. So it might be like 0.5, 0.1, 0.9. So what ends up happening is that this one is not very useful. You couldn't figure out what it was. Maybe it tried a rom-com or something and it just couldn't quite get it with the data that it has. But that's the beauty of it. So now you can, when you take this, right, originally, and now you break it up into this, you can make much better recommendations because now you can just grab, for all the users, grab the sci-fi column, recommend sci-fi movies for the ones that have high correlation. Do you see that? Now the diagonal is actually the other one. And this one is interesting because what it does, believe it or not, is that it's going to have values here. So it's going to have like 2.9, 9.5, 1.3. So basically we had 3 columns, 3 concepts, and in the diagonal, it basically provides a confidence of each column. So you can see the first 2 are 12.9 and 9.5. They're pretty high. So it's saying those are trustworthy. You can rely on them. But the last one, 1.3, I wasn't really sure, so better not to use it. So it even provides that, and that's actually in the matrix. So amazingly, you know, a matrix X, when you apply singular value decomposition, can be decomposed into these 3 matrices. And they just meet these properties. And that's the algorithm, singular value decomposition. So again, you know, I'm just giving you guys the intuition of it so that you understand where it's coming from. And in particular, so that you can interpret these 3, because you will have to interpret them, as I said. The last one, which I said was concepts to movies, was basically the same thing. So now you have the movies, The Matrix, and then you have Casablanca and Alien, right? So, and it's going to create, again, the concept, C1, C2. So this is sci-fi. And this is romance, right? So what's going to happen is Matrix should have a high correlation here, and Alien should have a high correlation, but Casablanca, which is, you know, not sci-fi, should have a low correlation. And then for the romance, Matrix, romance, kind of a romance, right? So 0.5, let's say, it's kind of like confused there. Alien, I don't think it was. So let's say 0.2, and then Casablanca 0.9. You see that? So it correlates these to the concepts. Again, I repeat, it's not gonna tell you sci-fi, but when you actually look at it, you'll be able to say, oh, it's sci-fi, or even more importantly, a category you've never identified, like rom-com. Maybe that didn't exist before, right? Maybe there was romance and comedy, right? And then over time, they were getting this column that was pretty strange. What is this thing that they seem to like? And then it turned out, well, it's somewhere in between rom and com, and they came up with the name rom-com. I wouldn't be surprised if that's how they did it, or some marketing person. But anyway, that's kind of how it works. Is this clear for you guys? Any questions? Yeah, go ahead, please. Huh? Cookies collect everything that you're doing. So you know, everything that you're doing online is being captured in some way. So, you know, they're capturing your clicks, right? So that basically says if they put ads, right? And there's an ad that you like, or you clicked on it, right? You don't have to rate it, you just have to click on it. So that's an endorsement that you like that ad and that it worked for you. So they're gonna store that as a rating. Yes, so you're right. Because what's the product there? More ads. Do you see that? If you let's say that you were in a week, you're online and you're looking at sneakers, right? So you look at one and then another one and then another one. They're going to learn that, and in their whole rating scale of advertisements, you're going to get another sneaker because they think this person's about to buy, and other people that followed your pattern, some of them bought this one. I don't know what's hip sneaker right now. Adidas, right? So they bought that one, what he bought. And he was looking at sneakers, you were looking at sneakers, guess what they're going to advertise to you? More sneakers of Adidas, the one you bought. Unless Adidas pays for them to advertise even without them liking it. So then, yeah, that may also happen, but that's just, you know, they pay. But otherwise, if it's just based on the pure rating scale, it'll be whatever he bought, they're going to recommend to you if you both have the same pattern. Does this make sense? Yeah. So it's actually, I would recommend you do that for your project, at least some of you, right? Consider, because for this homework, this is not a project, the homework for this will be for you to implement, or I'm going to give you the code for the recommender, but I'm going to do it for movie reviews. I want you to do it for something else. So advertisements, for instance, would be good, because you will have to demo this homework to me. So, I'll probably rate a couple of things, and then it needs to recommend something. So it could recommend an ad, recommend just something else. Books, yeah.
So in that chart with the samples rated like that,
Yeah.
can the computer, silly question, instead of giving it a 1 or a 0 in the y-axis, could it be a float value? Or is it always going to be?
Where? These are floats.
Yeah, I know they're floats, but that's a matrix of the vector. I've been saying at the end of, never mind, my bad. I answered my own question. It ends up putting those in the groups. That's how it decides whether it wants to recommend.
That's right. So it creates this concept, right?
Yeah.
And this is a sci-fi concept because Matrix is high, Alien is high, Casablanca is low. Yes. So then romance, actually Matrix was somewhere in the middle, Casablanca is 0.9, Alien is really low. So you see that of the two, this one is the more solid one. This one's a little bit more iffy, but still might. It's still going to do it. It's just the user that sees the matrix and then the system recommends Alien may watch Alien. Whereas the user that sees the matrix and the system recommends Casablanca may not see Casablanca because of it's black and white, whatever. So there's various reasons here, but this is the idea. Okay, guys? So is this clear? And by the way, the values could also even be negative. Okay, so that's something that I didn't say. So they could actually be negative, which is basically, it's like they really don't like that movie. All right, so that's definitely a possibility. Yeah. Not from the rating, but from the decomposition. The decomposition itself can give you negative values. Not the ratings is just a scale from 0 to 5, let's say. You see that? So you would rate from 0 to 5, but the system can actually, the singular value decomposition could give you negative values, which just says it's more strongly against the idea or the concept. So I think I've said everything. So that was the example. Is that clear? I mean, I just filled in some of the numbers, but I think obviously these numbers are not exact. I mean, they're not the numbers from this original data. I just made them up, right? But they would look like that. So remember, it's three matrices. So in summary, going back to the theorem, you have some data, right, that you got. It is M by N, where this is the users, user 1 all the way to user M. M. And then here you have the movie, 1, 2, all the way to movie N, right? And a matrix of this shape will be decomposed into 3. And then this one is, again, users to concepts. This is the diagonal, which basically remember, it's just the values in the diagonal itself, and it tells you the importance of the concept. Okay, so I explained that. And then the last one is, remember, this one is concepts to the movies themselves. So sci-fi, romance, etc. So the concepts are whatever they can be. The stronger ones will probably be, sci-fi, romance, action, something like that. And then there might be more complex ones like rom-com, where it comes up with different ones depending on what you like. All right, so that's it as far as the theory. Do you guys understand? Are there any questions before we move on? So the next step now is to look at the actual code and to implement it. So no questions, everything clear? You think you'll be able to do this? Yeah. All right, so let's then open up the Jupyter notebook then. Remember, because this homework is kind of important, it's one of the important things. It'll probably be due like 2-3 weeks from today, from Thursday or Wednesday. And what I want you to do is implement an actual recommender system. Okay, you'll have to find some data. So start looking at data sets of advertisements or whatever it is that you can think of. All right, so let's get started with the code then. Go ahead here. Now, I should say that singular value decomposition can also be used with, so remember, at the end of the day, we're taking data and we're transforming it, okay, right? I'm taking that original data and transforming it. One of these matrices, whether it's this one or that one, could also be used for something else, okay? If you think about it, what am I doing here? I'm taking the rows and the columns, right? And I'm converting it into rows and another set of columns. Do you guys see that? Right? And I went from users, maybe I have 90,000 movies in here, but how many of those are sci-fi of those 90,000 movies? A lot of them. So really all those sci-fi movies, The Matrix, Alien, Alien 1, Alien 2, Alien 3, Matrix 1, Matrix 2, all those can be just made into one single thing called sci-fi. You guys see that? So in a sense, if we just grab this matrix, it's basically a transformed version of this original one. but possibly with fewer columns, because instead of having the 4 matrix and the, I don't know, how many Fast and the Furious do they have? Like 10, right? So imagine 10 Fast and the Furious, they're all basically the same movie, chasing cars, right? So it just, that's then something, I don't even know what categories, like funny and action and car culture. So we basically can take a whole bunch of features and make them into one. You see that? And that's called compression. So we're compressing the data from being m by n to being m by k, where k is much smaller than n. Because think of it, Fast and the Furious, 10 movies versus one that says car culture movie. And you basically, if you like car culture movies and a new one comes in, and you're gonna watch it because you like them a lot, right? Do you guys see what I'm talking about? But that's another thing. So singular value decomposition can actually be applied to at least 2 things, right? So I'll kind of, before we look at the code, I'll just point that out. That's called, so singular value decomposition can be used for recommender systems, which is what we're talking about today. Right, systems, but also for data, what is called dimensionality reduction. Right? Why is it called dimensionality reduction? Well, remember, if you have a vector space of 3, and now you make it into a vector space of 2, you reduce the dimensions, the dimensionality. Do you guys see that? And so that's why it's called dimensionality reduction. But really what it translates to is, if you had n by m, you can transform this into n by k, where k is a lot smaller than m. And just think, if you get confused by this, just think about it. 10 Fast and the Furious equals 1 car culture movie. And that's your feature. But anyway, so that's next week, we'll cover dimensionality reduction with singular value decomposition. Today, we're just going to focus on recommender systems today and on Wednesday. Is this clear? Any questions? Clear. All right, good. So now we are ready then to look at the code. So I'm going to go ahead and stop this one. And now what I'm going to do is I need to share the code. All right, so if you look here, we're going to go to GitHub. And we are going to need, so here under singular value decomposition, just go there. And you can see I have the code for both, for recommender systems and for compression. Okay, so I provided the script already. Then I have a Jupyter notebook and also the Python script. We'll write out the script in class today. All right, but what's important, what we're going to look at actually right now is the data. Notice that the data you'll need to download to your environment. You can see here, there's a couple of files to look at. This is the data for movie reviews. So you can read the readme.txt file. This gives you information about where this data came from. This is from Movie Lens. You can see the URL there, http movielens.org, right? So it's a movie recommendation service, and they specialize in that kind of thing. This is just, they have a bigger set that's about 1 million recommendations, but to make it efficient on the computer, I just have 100,000. All right, so, but you can read through this to get more information about where the data set came from and all that. So let's take a look. So here they have links movies, ratings, tags. Okay. Now let's take a look. So let's start with movies, or actually let's start with ratings. You can see it's a big file. It's 3 megabytes. But you can see it here. It is. All it is, as I said, the user ID, the movie ID, the rating, and the timestamp. So you can see, for instance, user 1. It's all these are all the ratings. User 1 rated all these movies, and rated with those specific values. Okay, all the way. Oh, user 1 rated a lot of movies until here. Then user 2 comes in, and those are the ratings for user 2. Got it? This is kind of what I had done before. Now, given that we have the user IDs, we can't look up the users because for privacy, their names have been removed, obviously, but it doesn't matter. We just need to differentiate that they were users, right? That's all we need. If you were recommending, obviously, you would do that within your own system. Then the other file that we have is we have other data in here. We have movies, of course. So here are some of the movies. We have the movie ID, and then we have the title of the movie and the genre. So we kind of already have the genre annotated, but we're also going to infer some of it. So that, and at the end of the day, what we want is an automatic way of recommending something, right? So given some inputs, boom, recommend something. So here we have a few movies, so there's Casino and Ace Ventura, and then just a whole bunch of movies, right? So we've got the IDs. The other files, really, so we really, for this exercise, we really just need these two, because obviously, to know that it works, right? To know that it's doing a good job, we want to see which movie it's predicting, not just the ID. We won't be able to say anything by the ID, but if we look at the movie, we'll know, okay, yeah, this is a good recommendation. So we'll need these two files, the one with the ratings and the one with the movie. The other things, tags, I think it's just like a note. Yeah, so they have like, user 2 for movie ID, whatever this is, 60,000, set the tag was funny, right? So then you captured what they're saying. So they actually wrote a word. And then I think links is just something related to IMDb and some references for them. But we're not actually going to use this one, okay? We're not going to use this one. So really, we just need the two files, movies and ratings, okay? Got it? All right. So let's get started then. So I'm going to go ahead. I need to download those files. Download the file. Value decomposition. Recommender data. We're gonna just need ratings. Copy those to your folder. Actually, so singular value decomposition. And then in here, let's put in data. Let's just paste it. So we have now the two files, okay? So now the next step is, let's start the Jupyter Notebook. All right, so now we have, let's go here and let's go here. I need to share the Jupyter Notebook. So, okay, so we are in the Jupyter Notebook for the course, singular value decomposition. There's your data, right? So now what we need to do is we need to create the script. So I'm gonna just do it in here, singular value decomposition, new Python 3. So we've created our script. Okay, so the first thing we need to do is we need to try to bring in the data somehow. And there's actually a problem with that. Okay, so the problem is that for the users, there's no problem. There's about 620 users, and there are no omitted IDs. So really, the IDs go from 1 to 620. However, for the movies, there's about 9 to 10,000 movies, but the spread of the IDs is from 1 to about 90,000 movies. You guys see that? So that's a problem. Think about it. We have, if we go back to the whiteboard, right? So what I'm saying is we have about 620 users and about 9,700 movies. The IDs for users in the data set go from 1 to about 620. So that's no problem. But the IDs from here go to about 90,000. You see that? So we need to create a matrix that is users by movies. You see that? But we have, you know, the movie The Matrix is movie 3, but then Alien might be 87,000. But between 84,000 and 85,000, there's nothing. Those IDs were just not used. So one solution could be to just create a matrix that is 620 by 90,000. And then there's going to be a lot of zeros in there because for some movies, you know, they don't even exist. So that whole column of movie, let's say 8,500, there is no 8,500, but we will have a column 8,500. It'll just be full of zeros. Do you see that? Do you guys think that could be a problem? I mean, if the values are zeros, they're going to be ignored, right? So mathematically speaking, should work. But what could be a problem with that? Yes. Yes, and what? Yeah, how does that translate into your, you know, the processing time, right? So that's the question. Yeah. It'll take a lot longer, right? And you've learned from multi-layer perceptron and Weka that you never want to do that again, right? You don't want to spend days, right, doing something like this. So this is important because initially you're going to say to yourself, no, the code, if I just leave it at 90,000, the code is pretty easy. So I'm just going to use that code. Sure, that code is easy, but then it's like you're hurting yourself because you have a really large matrix. And this 620 by 90,000 is going to take a very long time to process and to give your results. Do you see that? So what you want to do is, if you have 9,700 movies or so, make it that size. Okay? So you need to then, it's like you're going to have to add an extra step where you take the movies that are 90,000, but map them to a scale from 1 to 9,700 or so. And this, it's, as I said, it's important because it's, you know, it's something that could run in 3 days will now run in an hour. And so a lot of the time, machine learning is like that. It's a lot of that. You have to be clever with your data to get results fast. Also, if you're in the stock market, right? what good is it to get your information a week from today? You want it now, because you need to make a decision about your investment now, not a week from today. So you got to do little tricks like this, okay? But it's actually pretty straightforward. It shouldn't be that complicated. We just need to we need to find a mapping function. So we're going to keep basically now, instead of one table, two tables. That's all it is. So the table that was from 1 to 90,000, now we're going to map every single one, right, to a table that is 1 to 9,700. Then we're going to use this to create our matrix, and then we have a much smaller matrix that has a lot less zeros. So it doesn't have as many zeros as it would have had before, and that's really good for your processing. All right, so now then we're going to end up with a matrix that is 620 by 9,700 or so movies. Is this clear, guys? Yeah. All right. So that's what we're going to do now. So let's take a look. So today, we're running out of time for today. So I'll just play with the data a little bit, and then we'll get into the code on Wednesday. If you think of, actually, as I said, running the singular value decomposition is pretty straightforward. It's just one line of code. What's really going to take a lot of work is honestly this whole process of the mapping, taking the data from the files, and then putting it in the format users by movies. That's really what's going to take a lot of the code, as you probably have seen. And also what I would recommend is before Wednesday, look over the code that I posted on GitHub, and then you'll have a better intuition when we discuss it on Wednesday. So let's switch over to the Jupyter Notebook, right? And then now we're going to use a couple of libraries. So NumPy, of course, this whole course is based, in this whole course, as much as I can, I do everything in NumPy. It's only like when we get to like deep learning that we have to use something called tensor keras, but otherwise I always keep it because, so we build things from scratch. All right, so we're also, I don't know if I've introduced this one yet, Pandas. I did, okay. Okay, great. So we're going to use Pandas today. Pandas will help us just to read in. It's a formatting library, right? So it helps us to read in data, take a look at the formats, etc. So now that we have this, we're going to use the movie lens data set, right, of movie reviews. Basically, the bigger one has 1 million, but if you want to play with that one, you can try it out. This one only has 100,000. And the website you saw is grouplens.org. Okay. So let's the first thing that we want to do is we want to get a sense for the data. So I'm going to look, my data is in the folder called data. So create a variable data. And we're going to call pandas, and we're going to say read underscore CSV. Okay. And then we're going to bring in from data our ratings .csv file. Okay, so that's the ratings CSV file. Remember the format of each row: user ID, movie ID, rating, timestamp. Okay, we need to bring in that data from that format and put it in the format users to movies. Okay, so this should read it. Let's try it. I'm gonna save this actually. Okay, no errors, so that should have brought it in. All right, so it found the file. So now let's take a look at some of the statistics of this. So one thing we can do is say users equal data. And then we can just reference the data by the column names. So the column names are user ID, capital I, ID, and also for the movies, data, movie ID. Okay, so first thing we want to do is let's just print it out. So let's print out users. There's about 620, so that shouldn't be too big. See, there they are, right? No, actually, hold on. Yeah, so the user was repeated, right? So if you guys remember in that ratings file, you'll see user 11111 for all the movies that they rated and the rating. So that's why it's showing about 100,000. So this actually gives us what? The number of rows that we have in ratings. You guys see that? Now, if we just want the unique ones, let's say we just want to know how many actual user IDs we have, right? We're going to type in unique. And then now I can do the same length of users, and it should give me about 620. Yeah. You see that? I printed them out. If I want the quantity, I can just say length. I'm going to save it, run, and see that, well, 610. So that's the number of users that we have. Got it? Questions? All right. So now the next one for movies is going to be the same thing. Let's print out the movies first. It's going to be a lot. Run it. You can see there 100,000 again because they're in that format. Let's get the unique ones. You can see it's got all of these IDs. Actually, it goes to 106. What is that? 163,000. So not 90,000. It's even larger than I thought, right? But that's a problem because it's very sparse, right? So you can see here it skips. So we'll need to do something about that. But we want to calculate the length of the movies to see how many we actually have. So I'm going to do length movies here. Save it, run. Parentheses. And there you go. So there are now 610 users, 9,724 movies. So we know for sure now the dimensions of our matrix, right? This is the matrix, the dimensions of the matrix that we're going to have to decompose now with singular value decomposition, okay? So that's basically the idea. We can also take a look at the data itself, just a little bit of it. So we can do print data head, and this will just give us about the first 5, I think. And you can see that there, right? So we got the user ID, the movie ID, the rating, and the timestamp. And so we will just need to process this. Okay, so so that was just for viewing the data. The next step would be now to read in both of the files that we need. So we're going to call it data ratings. Data ratings. And so we're going to do pandas dot read CSV. So it's going to be data ratings. CSV. And for the movies, data movies, pandas dot read underscore CSV. And this is located in data. And it's going to be movies. Let's see. All right, so I'm going to run this just to make sure that it finds the files. I'm going to go ahead and remove these print statements. They were just to kind of help us visualize things. Okay. All right, so there we go. So we've got the data now. Now, the next thing that we might want to do, I'll kind of end with this one for today, is we're going to need our matrix, right? So the matrix that we're going to actually decompose into three, that's going to be, let's just call it the ratings matrix, right? So that's the name we're going to give it. This is the ratings matrix. And we can just initialize it as a NumPy array. So we're going to say NumPy of zeros, right? And then we can just specify the dimensions that we want. So the dimensions of it are, we can say the shape, right, is going to be 9,724, which is the number of $9,724, and it was at 610. So as you can see, we can initialize the matrix with those dimensions. Does this make sense? And I think we can specify a data type. So these were integer basically because they were just 1, 2, 3, and 4, right? They weren't really. D type equal np dot uint. Okay, so that basically now if we print the shape, we can say print ratings matrix dot shape. So if we run this, and there it is. So it's got the dimensions 9,724 by 600. Got it? All right, so we can stop here for today, but we'll pick this up on Wednesday. So I'll continue, and then we'll basically implement. We'll read all the data from the CSVs into the matrix, apply singular value decomposition, and then hopefully try to recommend some movies. Any questions? No questions? All right. So I'm going to go ahead then and stop the question in the chat. All right, so I'm going to stop the recording now.